All right, so whenever you have probability of either an independent or a dependent event, whenever you have two events that are independent occurrences of one another, basically one doesn't have any effect on the other occurrence. So like if you toss a coin twice, the outcome of the first one has no effect on the outcome of the second one. Okay, so basically it's like nothing's tied to another, like the next event. Whereas, and we'll get into like dependent events, like if I have a deck of cards and I pull one card out and then I don't put it back in the deck, then the probability is going to change because I have one less card and one card's kind of like already out there on the table. So whenever we talk about probability of independent events, basically it's very similar to like whenever we talked about mutually exclusive type problems and where two things can occur and whenever you're going to multiply the probabilities of those two together. So if it says here, so it's kind of like Wheel of Fortune if you know what that is. It says you're playing a game that involves spinning the money wheel shown. During your turn, you get to spin the wheel twice. So what's the probability that you get more than $500 on your first spin and then you go bankrupt on your second spin? So first thing that you want to do or we need to figure out is how many spots do we have? So if we would zoom in here, we've got to figure out how many spots we have total, and then how many of those are more than $500. So not $500 and up, but anything above $500. So if we have anything that is above $500, basically that's all the ones that are marked with the letter A. Okay? We have 5,000, we have 650, 750, so on and so forth. So how many of them are above A? 8 out of how many total? So the probability of basically the first event happening is 8 out of, what do we say, 24? Okay, so the first event is anything above $500. All right? What is then the probability of going bankrupt? 2 out of the 24? So then what am I going to do with 8 over 24 and 2 over 24? What do I need to do with those two values? Multiply them together. So I'm going to take the 2. Huh? Oh, you can. That's fine. It's really up to you as far as if you want to reduce 8 over 24 and 2 over 24. I'm okay with that. If you want to make it 1/3 and 1/12, that's fine. So I wouldn't be opposed to it. I would probably I would do something like this and go. Just going to make it easier that you have a 1 out of 36 chance of getting something higher than 500 and then getting bankrupt on the second spin. So then the second one says during the 1997 baseball season, it says Florida Marlins won 5 out of 7 home games and 3 out of 7 away games against the San Francisco Giants. During 1997 National League Division Series with the Giants, the Marlins played the first 2 games at home and the third game away. Marlins won all 3 games. What's estimate the probability of this happening? So, does anything that happened before, like them winning 5 out of 7 or them winning 3 out of 7 away games, what's the chance of happening. So we're gonna use like experimental probability here in terms of going with what we know. Okay, it's not necessarily 1 out of 2 each time. Okay, but we're going to go with what we actually have as far as our experiment. We have data driven to give us already like kind of our answer. So each time that they play a home game, if we go with like previous experience, what's the chance that the Marlins are going to win? Like for them to win, what's the chance of them to win the first game if it's at home? How many games did they win during the season? 5 out of 7. So like for game 1, they would have a 5 out of 7 chance. Oop. For game 2, which is also at home, what's the chance of them winning? 5 out of 7. Then for game 3, which is away, what's the chance of them winning away? Bless you. 3 out of 7, right? So what am I going to do with 5 out of 7, 5 out of 7, and 3 out of 7? If we're going off of previous experience, obviously whenever a game gets played, normally you've essentially have a 1 out of 2 chance. You're either going to win or you're going to lose. Okay, it's 50-50. But if we go with previous experience, then what am I going to do if, like, I want to say, like, to predict, hey, they're going to win all 3 games or the first 3 games of this series? What's the chance of that happening? What am I going to do with 5 7s, 5 7s, and 3 7s? Multiply them all together. So I'm going to take 5 out of 7 times 5 out of 7. So I'm going to get 75 out of 343. Now, if I want to do, like, on this one, this would probably be something like, I would do about 0.219 or about 21.9%. Okay. Going off of, again, previous experience. Okay. Either of these would work. Third one then says you collect hockey trading cards. For one team, there are 25 different cards in a set. You have all of them, except for the starting goalie card. Okay. To try to get the card, you buy 8 packs of 5 cards each. All cards in a pack are different, and each of the cards is equally likely to be in a given pack. It says find the probability that you will at least get one starting goalie card. So in this case, you have 8 packs, so that means I'm going to have 8 different ways of doing this. So this kind of goes back to our combination that we have before. Okay? Could you get these are just packs of cards. Okay, could you get more than one goalie card? Like a pack of baseball. I don't even know if kids buy baseball cards anymore, or you get the idea. Okay? But I could get a whole pack of 5 goalie cards, right? Okay, that's a possibility. So, but it's all a combination. Order doesn't matter. It doesn't matter what the first card is, what the second card is of this pack, but it's just a matter of how I'm going to go about it. So then, what's the chance, first off, like for each, how many different combinations do I have per package? Like if I'm going to have to do a combination first to figure out how many total options that I have. So I kind of have to go back with previous knowledge and go, there are 25 players. How many cards in each pack? 5. So I have to find the combination of 25 different people. 53,130 different combinations. So this is how many combinations I have. What do I need to do then for each individual pack? How can I find the combinations of picking the goalie out of the 5 people? I can't pick him more than once, right? How many people are on the team? How many people are on the team? 25 people, right? How many people are not the goalie? 24. So what is 25 with a combination of 24? It's probably not as big as you think. Now, ready? Okay. There's only 25 different ways that I can pair this person with the other people on the team. Right? Okay. So, what I'm going to do is I'm going to take that 25 out of 53,130. And I'm going to take it to, instead of multiplying it by itself, because that's every single pack of cards. Like, that's the chance of getting a goalie in that pack. Okay? Because there are 25 different cards in the set. There's one card that I'm looking for. There's basically 25 different ways that I can pair that goalie with all the options. So instead of multiplying 25 over 53,130 8 times, I'm just going to take it to that 8th power, because there are 8 packs. Okay, so whenever I do that, whenever I take 25,000 divided by 53,130 and I take it to the 8th power, okay, it's going to give me an error. I want to take that from 100%, okay, because that's all the options. And I don't even know if you have the ability to do that. Nope, can't. So the probability of me getting this is just going to be 1 minus because I can't actually get a value. Like a calculator's not going to be able to give me this value because it's going to be way too small. Okay? Because that's 100% of the, like, all the options. Does that make sense? Yeah.
Why did you do 25
Because there's, like, if I have, say I have 25 people in here, and I need to put groups of 5 together, I can't repeat you again in a group. Does that make sense? So there's 25 different people that I can pick from. I just want to make sure I'm only looking for the one time, like, or really all the times that like you would be in a group. Like if I pick these three and these two, I'm not worried about that group. Does that make sense? Because you're not in it.
Yeah.
Whereas if you're in it and then like I go with Daniela and I swing this way, that would be one of the 5 or one of the 25 that I'm worried about. Okay? Does that make sense? Because I'm not repeating anybody. Like I can repeat them throughout, but like if I have like you and Colin, then I would have 3 people, but I can't repeat that group again. Does that make sense? Because there's only going to be those 25 because it doesn't matter the order in which I put them. Okay? Then whenever you have dependent events, it's basically that one thing's going to affect another. Okay? So it says the probability that B will occur given that A has already happened is what's called conditional probability. It's going to have B and then it's going to look, it's not division, but it's going to have like a bar and then A. Okay? Whatever my first event is. So I'm going to take those values and still multiply them. But all this, like the second part really means is that there's a change in, like, normally like the number of outcomes that I have or the number of total events. Okay? So really this is just meaning that there's a change in the original probability. So like if I have 52 cards and I draw one card, but I don't put it back in the deck, how many cards am I is the other person holding now? 51. Okay? So it's like if I don't draw that card, like if I take one out and I'm looking for one specific card, originally whenever I did that, if there were 52 cards and I pull one out, I've got a 1 out of 52 chance of finding the 7 of hearts. If I pull one card out, but I don't put it back, and the card that I drew out's not a 7 of hearts, the probability of me drawing it is going to go to 1 out of 51, right? Okay, it's kind of like whenever I don't replace something, like if I don't draw it and then put it back in the pile or put it back within there, okay? Or if I take 2 blue M&Ms out of the jar and I eat them, are there 2 blue M&Ms still in the jar? No, they're gone. Okay, there's 2 less M&Ms in the jar or the bag or whatever, okay, because things don't get replaced back in there. Okay, so like your chances are going to change, and normally what will happen is they're going to go up. Okay, your probability, instead of like replacing it and putting it back in there, because you have less events or less options, I guess is the right way of putting it. It says the table shows the number of endangered and threatened animal species in the United States, November 30th, 1998. Find the probability that a listed animal is a reptile, and B, the probability that an endangered animal is also a reptile. Okay, so before you even go, so the first thing, what's the chance of you having an animal that is a reptile? Okay, so how many reptiles do we actually have? 35. How many total animals are there? Well, what are you going to do with all those numbers? Very good. So if we add up all those numbers, first off I have 35 here. If I add everything else, there is 68, that's 90. Oh, that's only 8, not. 47. So add everything up. Where are we at total wise? What was it, 475? So the first thing, what's the chance if I just pick any animal, what's the chance of it being a reptile? What am I going to do? 35 out of, so if I'm just looking for any reptile, so as far as like part A, all I'm really looking for is 35 out of, I've got a 35 out of 475 chance that it's going to be a reptile. Okay, if I would, so about 7 out of 95, which is about 7.4% chance of happening. Whereas whenever it says what's the probability that then we have an endangered animal that is also a reptile. So from here, how many endangered animals do I have? What do I need to do with, am I going to take everything out of 475 animals? No, which one am I looking at? I'm only looking at this category here, right? Okay, I'm only looking at the top side. So then I would need to, basically, this is like a two-way table, essentially. Okay, as far as like total mammals, total birds, total reptiles, total amphibians, so on and so forth. And then I would have all the total endangered animals, which is going to be 355. So then what's the chance of me getting an endangered animal that is a reptile? 14 out of 355. So 14 out of 355 is about 3.9%. Then on 6 it says you randomly select 2 cards, 52 card deck. Okay. What's the chance of you getting a card that is not a face card? So king, queen, or jack. So how many of them are not face cards? Well, how many cards are there? 52. How many of them have faces on them? 12. So what's 52 minus 12? 40. So 40 out of 52 are not face cards. So if you do the second card, so same thing where then like, so if I'm doing part A, first chance I have to draw a card that's not a face card is 40 out of 52. And then the second card is a face card. So then how many face cards are there? 12. It says on A, it says you replace the first card before selecting. So I draw it, look at it, not a face card, put it back in the deck. So did the number of cards in my hand change? No, I still have 52, right? So then if I still have 52, what's the chance then of it being a face card? 12 out of 52, right? So if I take one, so for this to happen, I'm going to take one, look at it. It can't be a face card, so it can be any of 40 cards. Put it back. Then the next one I want to draw is out of that 12. So whenever I do this, again, you can simplify 40 out of 52 if you want. You can reduce it. You can multiply them straight across. It really doesn't matter to me. I'm looking at about 30 out of 169. or a chance of about 17.8%. What's going to change on part B if I don't replace the card? So if I draw the card out and I leave it on the table and the other person's still holding the deck of cards. So it's still 40 out of 52 because that didn't change as far as the starting spot. Okay, so as far as part B, it's still 40 out of 52 for me to draw a non-face card. What's the chance if I draw one out, I didn't take a face card away, so what's the chance of me drawing a face card the second time if I did not put a card back into the pile? 12 out of 51. Because I didn't put a card back in the pile? So then 40 out of 52 times 12 out of 51. So 40 out of 221, which is about about 18.1%. Now, what if I was trying to, and I'm going to kind of play the what if game here, what if it would have said to draw back-to-back like face cards? Like what if I wanted to draw a face card first and a face card second and I didn't take it out? What would be the chance? Like what would be the first chance? It would be 12 out of 52, right? What would then that change as far as the second card? 11 out of 51. Okay? So in some cases, depending on what you're dealing with and what you're talking about, some things may change just one value, some may change both of them. Okay? Like if you want back-to-back of the same thing to happen, okay, then most likely both things are going to change. If things don't, like if you don't want the same occurrence twice in a row or 3 times in a row, then only usually your total's going to change.